Here we learn application of Fourier series. So let's do it for the mass spring system. So here I have a mass on the spring. So let's draw the spring here. And we have the mass. The spring with the stiffness K. So the hook constant K. And the mass M. We have an external force, say F. F depends on time. So here's our system. We have the ODE correspond to the system. M times X double prime K times X equal to FT. We want to solve it for X. Now 5XT. This is a non-homogeneous system. So XT will be X homogeneous part plus X particular part. So we will find the homogeneous part first. X at T. We also call it a complementary solution. So that is when we have the right hand side 0. And this one particular solution. For the homogeneous part, X homogeneous D, which is a solution of mx double prime kx equal to 0. So we know that's X homogeneous. Let me just write X for now. XT of the form E lambda T. X prime T lambda E lambda T. X double prime T lambda square E lambda T. Plug in this equation 1. You get M times lambda square E lambda T. K times E lambda T is 0. You have this in common. It's never be 0. You can divide both sides by that. M lambda square K equal to 0. M and K are given to us. We find lambda. Lambda square minus K over M. So this one is negative. Lambda is plus minus I square root K over M. Square root K over M denoted by omega naught. This is the natural frequencies of the system. X system has a natural frequency, and we have lambda is plus minus I omega naught. So the homogeneous part H. So it's a combination of two solutions. We have E power I omega naught T, and you have the second one E minus I omega naught T. So the linear combination gives us H C1 E I omega naught T, C2 E I minus I omega naught T. You can write down in terms of sine and cosine using the Euler formula. E I theta, cosine theta, I sine theta. So this one you can write as in terms of sine cosine of omega naught t. And say if I have big C1, big C2, I can write down as something small c1, small c2, like x8 small c1 cosine omega naught t plus small c2 sine omega naught t. You use this formula, you will bring it to this form. So remember, this C1 are different. Write down this is big C1, this is big C2. So by using the Euler formula, you bring this into this form. So this is a homogeneous part. Now we find out the particular solution. So xt equal to the homogeneous part or the complementary solution plus x bt. We will use Fourier series methods to compute this. So now let's look at the system. We have this one. We will find the so-called steady, find the alpha A steady periodic solution. So we will find the special one for xp. I call it x steady periodic xspt using the Fourier series methods, periodic particular solution. And we use Fourier series. So usually they will give us the function f is periodic. So say for this question where ft is an odd function, with period 2L. And for odd function, you know the Fourier series. The Fourier series of ft will contains only the sine terms. Fourier series of ft, we have summation bn sine n pi t over L, n from 1 to infinity, where bn is 2 over L, 0 to L, ft sine n pi t over L dt. So this is our Fourier series for big F. Now we use Fourier series methods. You write down x as Fourier series. xt. We also use the odd function. So I write as summation of small bn sine n pi t over L, n from 1 to infinity. And you try to get the formal Fourier series solution. You compute this one, you plug in here. X double prime t, you do it terms by terms. Bn, so actually minus bn because we do 2 times. N square pi square L square sine n pi t over L. And plug in this system. We have m times n times this plus k times x equal to ft. So m times x double prime k times x equal to ft. Now we get all the coefficients of sine n pi t and let coefficients equal. So we have m times the summation, I write out as summation n from 1 to infinity. M times minus m bn pi square n square L square k bn. So you can bring bn out because this is also in common. bn sine n pi t over L. Inside you have minus this plus k. This is the left hand side. This is our left hand side equal to the right hand side. So we have both sine n pi t over L. So let's coefficient this one equal to bn for all n. For all n greater than or equal to 1, coefficient here on the left equal to the coefficient on the right. Remember that big Bn is computed using the forcing terms. So we have for all n greater than or equal to 1, somethings times Bn equal to big Bn. So under the condition this something's non-zero, we can find small bn. So we need minus m times this plus k. We want this one non-zero for all n greater than or equal to 1. If we have this condition, then we can find bn. Then bn is equal to big Bn divided by that. So now let's see the condition we have. So this condition is equivalent to n square pi square L square is different from k over m. Remember that k over m is a natural frequency of the system square, right? Recall that we have omega naught square root of k over m, natural frequency of the system. So as long as we have this condition for all n greater than 1, so which means that omega is not non-zero, actually is always positive, n positive, pi positive, L is also positive. So you can square root both sides. N pi over L different from the natural frequency of the system for all n. Then we can find Bn. So under this condition, we found Bn. And with this Bn, we have the solution x steady periodic t, which is a summation small bn sine n pi t over L, and from 1 to infinity. So yeah, with Fourier series, we found the steady periodic solution, which is this one. Remember that the condition we need is n pi over L is different from omega naught. For all n greater than equal to 1. In general, the steady periodic function, say for the system mx double prime kx equal to the force ft, so m the mass, k the spring constant, and we have omega naught, the natural frequency, square root of k over m, then the steady periodic s p x s p t. We can use the Fourier series method to compute that. Summation a naught over 2 summation n from 1 to infinity is a n cosine n pi t over L, bn sine n pi t over L. The methods as we have done before. So we write down the Fourier series of the Foxing terms. You write down the Fourier series of x. You do derivative here, terms y, differentiating this, and you equate the coefficient of sine, cosine, left hand side equal to right hand side. You get this. And remember that we need the condition that omega naught, the natural frequency of the system, is different from n pi over L. We need this condition for all n greater than equal to 1. Because if not, we cannot divide it by this. So if this is 0, then this one will tend to infinity. The system blow up. So in that case, we have the so-called resonance. So the mass blow up, the system will break.